Welcome to Chapter 3, specifically 3.1 on complex numbers. This photograph here is something I took when I was hiking across Italy. And it was just this really interesting morning. I got up early and I was staying high on a mountaintop. And there was this mist everywhere. And as you were climbing off the mountaintop, the way the sun was shining, you could see across the side of the mountain in the valley, and you could see thousands upon thousands of spider webs like you see on this plant. It was a little bit creepy, but it was really glorious, and it was amazing how many spiders there were out there. And I tried to capture this one photograph. It's a favorite of mine. Again, we're going to have a brief pause. Today we're going to talk a little bit about success. Success is no accident. It is hard work, perseverance, learning, studying, sacrifice, and most of all, love of what you are doing or learning to do. When I look at my own trajectory, when I was in high school, I thought I wanted to be a teacher, but I was actually advised by the guidance counselors against this. Um, Mainly because of the low pay in K through 12 teaching, and also the fact that teaching jobs at that time in the 80s were not always easy to find. And so being good in math, I was advised to go into engineering. It was a guaranteed job. You were going to start out at a high pay. And I was good at math and science, so I just listened to what the adults told me. um, but I realized later in my career, or actually after my sophomore year, that the stuff that I was studying, I really didn't have a passion for, and I just made it through. And I think it's important to think about the kind of work you want to do, the kind of life you want to live, and start with that. And I kind of had this mindset that this was just more school and it's what I've been doing all my life. And so I just kept plodding through and never stopped to ask, to kind of think about where I was heading. And by the time I figured that out, really between my sophomore and junior year, I felt I was too far committed into the engineering program. I had taken a lot of engineering classes that wouldn't transfer into another major. And so I finished with a degree in engineering and then went directly into an MBA program. I did do some technical work for a few years, but eventually, as you can see, made it back to teaching, which is kind of interesting. Put your heart, mind, and soul into even your smallest acts. This is the secret of success. I think this is another great aspect of success, is that there are no small things. And I think even Mother Teresa said something like she didn't do any big things. She just took a lot of care in all the small things that she did, and it made a huge difference, as we know. So even things like perhaps math is not your thing. This is just a bridge to get to someplace in your career. It's something you need for your major. Even focusing here and trying to do your best will help you in success in other places. One of the things I tell students often who hate math or don't think they're good at it is, imagine if you get an A in this class where you don't like it or you don't think you're good at it. The confidence that will come from that, because you know the things that you are good at, the things that you love to do, will come so much easier to you. And really, math is a great exercise because it's really about discipline and practice. And really, a lot of life is about that. Finally, failure is not the opposite of success, it's part of success. Students who are doing poorly or maybe even fail the class often apologize to me. And I always tell them, two things. First of all, you don't need to apologize to me. I have no idea why you failed this semester. Only you do. Perhaps there was something going on in your work life or in your personal life that pulled you away from being successful. Perhaps you were just lazy. Perhaps you didn't have the discipline and the skill sets to focus on this work yet. And so I don't have any judgment around failure at an individual level. I do have a judgment that failure is a necessary part of life. You will fail at things. You will drop the ball. You know, we all do. We do it throughout our career and throughout our life, and it's just a part of success. Learn from that failure, try to do better, and it becomes a strengthening, if you will, a strengthening, if you will. In fact, if you think about working out, what you're trying to do is get your muscles to fail, lift so much weight that your muscles fail, that your body then builds that muscle up. So today we're looking at complex numbers. This is kind of what I always call the Disneyland of mathematics. We're going to learn how to do computations involving complex numbers. Complex numbers are imaginary numbers. You've heard of real numbers, 1, 2, 3, 1.5, 2/3, etc. All of these are real numbers. They represent things in the real world. Complex numbers are made up of real numbers and an imaginary part. And we use these in math because they allow us to solve some expressions in math that would not be able to be so easily solved without this it's a cheat, if you will. It's like a cheat in a video game to allow us to kind of figure out what's happening with certain math expressions. So when you look at a graph, some functions have zeros that are not real numbers, okay? So remember, a zero is when the graph crosses the x-axis. The complex number system is used to find zeros of functions that are not real numbers. When looking at a graph of a function, if the graph does not cross the x-axis, then it has no x-intercepts, and thus it has no real number zeros. So no zeros that are real numbers. But it does have at least one complex number, 0. Okay? So the imaginary number I. The number I is defined such that I equals the square root of -1. And remember, we cannot take the square roots of negative numbers. So this is something we're adding to our math ability, or adding to our math toolkit. And these are the definitions. I equals, by definition, the square root of -1. And I squared equals -1. And again, that goes by the definition of a square root. A square root squared equals the radicand, or what's inside. Okay? So let's figure out how we can express each of these negative square roots in terms of I. Let's look at the first one, the square root of -7. So if we think about -7 as -1 times 7, we can separate these out as the square root of -1 times the square root of 7. And by definition, the square root of -1 equals I. So this answer is I times the square root of 7, or square root of 7I. I prefer that you write it the first way, because then it's clear that the I is not inside the radical, and sometimes the square root of 7I looks like the I is also underneath the roof, if you will, of the radical. So you can see that what that does is the I, when we pull the I out, it pulls the negative out. So for example, the square root of -16 is the square root of -1 times 16, or the square root of -1 times the square root of 16. And of course, this gives us 4I, because the square root of 16 is 4, and the square root of -1 by definition is I. Okay? Let's look at the next one, the negative square root of -13. Pay close attention to this example because this is one that a lot of students have troubles with, okay? So we're going to do it the same way, -1 times 13. Well, this is, don't drop the negative in front, negative times the square root of -1 times the square root of 13. And again, the square root of -1 is by definition I. So we get -I square root of 13, or negative square root of 13I. These are both the same. It's just putting the I in front or in the rear. Typically with variables like x, we always put it behind, like 2x, etc. But here when we have a radical, sometimes we put it in front because it's less confusing again. All right. Let's do the same thing with the negative square root of negative 64. We can see here that we have negative times negative 1 times 64 inside the radicand. This is the negative square root of negative 1 times 64. In the red, the square root of negative 1 is I. The square root of 64 is 8, so we have negative 8I. Let's look at one that's a little more complicated. We have the square root of negative 48, which again, if we separate out the negative 1 times 48, this gives us negative 1 times the square root of 48, excuse me, the square root of negative 1 times the square root of 48, and we get I for the square root of negative 1. But notice that 48 is 16 times 3, okay? And that's why I can simplify this even further. So the square root of 16 times the square root of 3, and the square root of 16 is simply 4, so I can pull a 4 out as well. And we do need to go down to the simplest version, and so we get 4i times the square root of 3, or 4 square root of 3i. Either way, it's fine. So those were our imaginary numbers. A complex number, as I said, is a number of the form a plus bi, where a and b are real numbers. The number a is said to be the real part of a plus bi, and the number b is said to be the imaginary part of a plus bi. And that makes sense because you can see the b is with the imaginary number I. So an imaginary number has a plus bi, and this is where a is not equal to 0 and b is not equal to 0. Okay, so this is really an imaginary number with a real part and an imaginary part. If you have a pure imaginary number, all this means is that a is equal to 0. So if I drop off the a, I just get bi. But b can never be equal to 0, or we will not have a imaginary number. If b is equal to 0, we just have a real number, right? Because if this goes away, 0i, we just have the number in front. Okay? So here are some examples for imaginary numbers. We have a equals 4 and b equals negative 2, so we have 4 minus 2i. Here we have a equals 3 and b equals 5, and we get 3 plus 5i. These are examples of imaginary numbers. If we're looking for a pure imaginary number, we have a equals 0, b equals negative 2, so we get 0 minus 2i, which is just, actually this is wrong, this should be a negative 2i there. I'm not going to correct that, I'm just going to trust that you're listening. This is negative 2i, minus 2i. Okay, so when we're dealing with complex numbers, they obey the commutative, the associative, and distributive laws. And the good part about this is they're going to act just like when we add other variable expressions, okay? We add or subtract them just as we do binomials. As you can see at the bottom, on the left I have 3 plus 2x plus 4 minus 3x. If I just replace the x with I, we're really going to do the math the same way between these two different math operations. We collect the real parts and the imaginary parts of complex numbers just like we can collect like terms in binomials. So when we're adding or subtracting binomials, we add the real parts or the constants, 3 plus 4, and then we add the like terms that also have the same variable and the same exponent, a positive 2x and a negative 3x, and then we simplify and get 7 minus 2x. We will do exactly the same thing and get the same kind of answer, 7 minus I, just like we got 7 minus x. So don't sweat these out. These are pretty straightforward, and you know how to do these with binomials and with variables, so the addition and subtraction should be pretty straightforward. If it is subtraction, make sure that you distribute it across the second term. So we can see that here. Let's look at some of these. I'm going to go through these pretty quickly because I think these are more straightforward. So again, if I have 8 plus 6i plus the other imaginary number 3 plus 2i, then I get 8 plus 3. I add the real parts, 8 and 3. I combine the imaginary parts, plus 6i and plus 2i, and this whole thing is a sum. So I'm going to add it all together, and I'm going to get 11 plus 8i. 11 plus 8i. 6 kittens and 2 more kittens gives me 8 kittens. 6 eyes and 2 more eyes gives me 8 eyes. Okay. So be careful here. Again, we have 4 and negative 6 because it's 4 minus a 6. And then we have a positive 5i minus a minus 3i. So that becomes 5 minus a minus 3i becomes 5 plus 3i. Okay? And when we've done that, we substituted a plus here. I mean, you could put a parenthesis there, but it's going to get confusing. So you want to think about what each of these is. So this is a positive 5i. We're going to add all these terms together. And then I have a minus 3, which will be a positive, but here you can see the step there. And we get negative 2, 4 minus 6 is negative 2, and 5i minus a minus 3i is 5i plus 3i, which is 8i. When we're talking about multiplication of complex and imaginary numbers, this gets a little bit more involved. When the square root of a and square root of b are real numbers, then when we are multiplying them, we can simply multiply them together underneath the house. So the square root of a times the square root of b equals the square root of ab. But this is not true. This is not true when the square root of a and square root of b are not real numbers. Okay? And it's important to remember that I squared equals negative 1. This is something we saw from the definition of complex numbers. So let's look at some examples and see how this works out. Okay? So in A, we have the square root of negative 16 times the square root of negative 25. What we want to do here is to first convert these into imaginary or complex numbers with the I. Okay? So here we get the square root of negative 1 times the square root of 16 times the square root of negative 1 times the square root of 25. Remember that the square root of negative 1 is I by definition. So we have I times 4 and I times 5. Thus we get I squared times 20. I times I is I squared and 4 times 5 is 20. But remember that I squared is negative 1. So we get negative 1 times 20 or negative 20. Okay? If we had put these both inside the same radical, we would get the square root of 20, but we would have multiplied the two negatives and got a positive. And that's where the difference is that we just talked about. You cannot combine them in there. You have to turn the square root of negative numbers into an I format and then multiply. Let's get these more complicated ones. And here I put your note there to remember that I squared is negative 1. So here we have the multiplication of two imaginary numbers, two complex numbers, a real part and an imaginary part. So what we're going to do here, just like when we added or subtracted complex numbers like we did binomials, this is going to be like a FOIL, okay? Now I don't like FOIL so much. I prefer to use a multiplication box. Because then you can use this box even if there are 3 or more terms like polynomials, etc., to multiply them out by just adding another row or column. Okay? So how to use the box? You put the first binomial, it doesn't really matter which one, you put one of the polynomials, or in this case one of the complex numbers, across the top, 1 plus 2i, over top of each box. And you put the other complex number or polynomial down the side, 1 plus 3i. What you have in here is simply a multiplication table that you remember from elementary school. You multiply what's on the outside edges and put it in the box. 1 times 1 equals 1. 1 times positive 2i is positive 2i. 1 times positive 3i is 3i. And positive 2i times positive 3i is positive 6i squared. Now we empty the box by simply adding all the terms. 1 plus 3i plus 2i plus 6i squared, and now we'll simply simplify. Okay? Remember that I squared is -1, so this becomes a -6. 1 minus 6 is -5, and 3i plus 2i is +5i. And so there is our answer to this multiplication problem. Okay, so we're going to do this like a FOIL, and here's another way of looking at FOILing by using a multiplication table. Okay, remember that 3 minus 7i squared is really the same kind of structure as what we have in problem B. This is not 3 squared minus 7i squared. Okay, this is the most common mistake I see in students. They square the first term, they square the second term, and then put some sign between them. No, it is again a FOIL problem. 3 minus 7i on the top, and I've made another mistake here. And no, I have. I'm sorry. This is 3 minus 7i squared. So 3 minus 7i on top times 3 minus 7i on the side. 3 times 3 is 9. 3 times negative 7i is negative 21i. Negative 7i times 3 is negative 21i. And negative 7 times negative 7 is 49, and I times I is I squared. Again, I find the answer to this box by adding all the terms. 9 minus 21i minus 21i plus 49i squared. And I get 9 minus 42i plus 49i squared. But I'm not allowed to have an exponent on the I, and I know that I squared equals -1, so I replace I squared with -1, and I get 9 minus 42i minus 49, which simplifies to -40 minus 42i for this problem. Okay, so remember when you're multiplying these out, if they're in radical form, you have to turn them into the I format. If you have polynomials with what look like polynomials or binomials, make sure that you are FOILing, okay? Especially when you have a square here, okay? This is a FOIL. This is 3 minus 7i times 3 minus 7i. We're also going to look at how do we simplify powers of I. Recall that when you raise -1 to an even power, -1 to the 2nd, the 4th, the 8th, the 22nd, you will get +1. If you raise -1 to an odd power, -1 to the 3rd, -1 to the 21st, -1 to the 105th, you will get -1. Okay? So this is an important rule to remember. Simplifying powers of I can be done then by using the fact that I squared equals -1 and expressing the given power of I in terms of I squared. So we're going to rewrite each of the terms we're given in terms of I squared, and then we can simplify. But let's look at the iteration first. Well, we know that I to the first power is equal to the square root of -1. I squared is equal to -1 by definition as well. Well, I cubed, we can rewrite, we can re-express I cubed in terms of I squared. I cubed equals I squared times I, right? There's 3 of them, I. Here we have I times I. And remember that I squared equals -1, so we get -I. In terms of I to the 4th, this is equal to I squared times I squared, which equals -1 times -1, or +1. At I to the 5th, we get I to the 4th times I. Well, I to the 4th was 1. We just saw that. We could have gone through this iteration too. Times another I, and we get I. Notice what's happened is we're going to go back through the same iteration. And so the powers of I cycle through I, -1, -I, and 1. Notice that when the exponent is even, 2 or 4, we have -1 or 1. Okay, so even exponents give us a real number, 1 or -1. Odd exponents, here's I to the first power, I to the 3rd power, and I to the 5th power, will be in terms of the I variable. So that's kind of a clue when we're looking at these higher powers. For example, if I had I to the 73rd power, I would know immediately that my answer is either going to be positive or negative I. If I have, because that 73 is an odd exponent. If I had I to the 74, I would know that because 74 is an even number, that my answer will be 1 or negative 1. When you have to reduce powers on I, know that your answer is going to be one of these four answers. Okay? You will never leave an exponent on I. If you have I cubed, I fourth, I eighth, you've done something wrong. You need to simplify it to one of these four. I, negative 1, negative I, and 1. So let's see how we do this. So let's look at the first one, I to the 37th power. Okay, so I to the 37th power is I to the 36 times I, right? Why did we do that? Because we want an even power here, because we now want to write I to the 36th in terms of I squared. Well, I to the 36 is I squared raised to the 18th power. 2 times 18 is 36. Okay, and remember, a negative 1 raised to an even power is equal to positive 1. So I get, I squared is negative 1. So I get positive 1. Negative 1 to the 18th power is positive 1, or simply I in this case. So I to the 37th is the same thing as just simply I. Okay, and again, we should have known that since the exponent was odd, we knew that our answer should be positive or negative I. In B, we know our answer, since the exponent is even, should be 1 or negative 1. I'm also going to show you kind of like a cheat for solving these as well. If you take the exponent and divide by 4, whatever remainder you have will be one of the first 4 exponents. 1, 2, 3. Of course, it can't be 4 because we're dividing by 4, or 0, and we'll look at that. Okay? So if we divide the exponent 37 by 4, we get 9, remainder 1. Well, this is the same. The remainder is the exponent on I as your answer. Well, I to the first power is simply equal to I. This, again, I've made another mistake here. This is I, not 1, okay? I to the first power equals I, not 1, as you can see here. When we do I to the 58th, I to the 58th, rewriting it in terms of I squared, 2 times 29 is 58. Well, again, I squared is negative 1. Negative 1 to an odd power is simply negative 1. Okay? Let's try our shortcut here, our cheat method. 58 divided by 4 equals 14, remainder 2. The remainder is the exponent on I, so this remainder 2 goes on I. So I to the 58 is the same as I squared, and we know that I squared is negative 1. Okay? Let's look at the next example, I to the 75. Again, we're going to take one I out so that we have an even exponent, so we can rewrite it in terms of I squared. I to the 74 is I squared raised to the 37th power, because 2 times 37 is 74. Okay? Don't drop your I there. We still need that I. Well, I squared is negative 1. Negative 1 raised to an odd power is negative 1. So we get negative 1 times I, or simply negative I. Again, looking at our cheat, 75 divided by 4 gives us 18, remainder 3. The remainder is the exponent on, I'm sorry, I made another mistake. The remainder is the exponent on the I. This is I cubed, which is equal to negative I, right? You should know those first 4 iterations. Or I squared times I, or negative 1 times I, etc. I added these boxes in here to the canned slides, and I'm sorry that I didn't pay a little bit more attention. So when we do I80, this is I squared to the 40th power, which is negative 1 to an even power, which is positive 1. Okay, I did it again here. So 80 divided by 4 is 20, remainder 0. The remainder is the exponent on I, not on 0. It's the remainder is the exponent on I to the 0 is equal to 1 because anything to the 0 power is going to be equal to 1. Remember, that's a rule of exponents. So you can use this kind of division tactic with just dividing the exponent by 4 and using the remainder on I and then converting that, assuming you remember the I squared, I cubed, and I to the 4th. So probably the most complicated part of this complex numbers are these conjugates. The conjugate of a complex number, a plus bi, is a minus bi. The numbers a plus bi and a minus bi are complex conjugates. Okay. Notice the only thing that's changed here is we've moved from addition to subtraction, or if we were given the subtraction to get its complex conjugate, we would turn it into addition. The sign of the first number, the sign of a, does not change. We are simply adding bi or subtracting bi. Okay. And that pair of addition and subtraction makes it a conjugate. It's not about the signs. You don't change all the signs to positive or negative, etc. You change what's happening in the middle. Is it addition, then it becomes subtraction, and vice versa. Okay? So for example, negative 3 plus 7i and negative 3 minus 7i are complex conjugates. Notice again, we did not change the polarity of a. 14 minus 5i and 14 plus 5i. If we have 8i, remember this is 0 plus 8i, so we also have negative 8i or 0 minus 8i. Okay? The product of a complex number and a conjugate is a real number. If I multiply these two out, I will get a real number, any of these pairs. When you multiply the complex conjugates, you will no longer have a complex number, you'll no longer have an imaginary number, you will simply have a real number. So let's look and see how that works. So 5 plus 7i times 5 minus 7i is a FOIL again. We're going to multiply these out. I'm going to show you the box again. So 5 plus 7i on the top, 5 minus 7i on the bottom. Again, this is simply a multiplication table. 5 times 5 is 25. 5 times 7i is 35i. 5 times negative 7i is negative 35. And positive 7 times negative 7 is negative 49. I is I squared. Okay? Notice that when we add these on the diagonal here, we have negative 35i and positive 35i. If we add them, these cancel out. And that's why we end up with no I terms, okay? Because the i's will always cancel out when you're multiplying conjugates. So we simply have 25 minus 49i squared. Okay? Remember that I squared is negative 1. So when we multiply that out, we get 25 plus 49, or simply 74. If I have purely imaginary numbers, I can simply multiply these out. I do not have to use a multiplication table. 8 times negative 8 is negative 64. I times I is I squared. I squared is negative 1. And so in this case, I simply have 64. Okay? So again, as long as you know how to FOIL or you know how to use this multiplication table with these polynomial looking complex numbers, this is a pretty simple process, but it's simple but not necessarily easy. It's easy to make mistakes. So take your time with these, use scratch paper, slow down, and check your work. So the conjugates get really kind of confusing when we're doing division, and this is really where they come into application as far as why we do this with a lot of math problems, okay? So what we're going to do is we're going to write the division problem into fraction notation. Notice that 2 minus 5i, notice that divide 2 minus 5i by 1 minus 6i is 2 minus 5i in the numerator over 1 minus 6i in the denominator. Then we're going to multiply by 1. Now, we're doing this in fraction notation, so as long as we have the same thing on top and the same thing on the bottom of a fraction, we are technically multiplying this fraction by 1. And what we're going to do that is use the conjugate of the denominator, the conjugate of the denominator. And remember, when we multiply by conjugates, we get a real number. And that's what we're really shooting for here, is to get rid of the imaginary number in the denominator. So here's we set this up as division, 2 minus 5i divided by 1 minus 6i. But when we're doing division with complex numbers, we multiply by 1, and that's this part over here in red. 1 plus 6i over 1 plus 6i. Notice this is the conjugate of the original denominator. We change the minus into a plus, and now we can multiply. Okay, this is a FOIL on top and a FOIL on the bottom, and so you need to either do two multiplication tables or FOIL it out. We end up getting 2 plus 7i minus 30i squared in the numerator. I'm not going to do the FOIL on this one. You can do that on your own. Divided by 1 minus 36i squared. Again, I'm not doing the FOIL either. We've done enough today. So you can try those and make sure you get those. Well, 30i squared minus 30 times minus 1 is plus 30. And 36 times negative 1, negative 36 times negative 36 is positive 36. And so we end up with this form over here, 2 plus 7i plus 30 over 1 plus 36, which gives us 32 plus 7i over 37. 32 plus 7i over 37. Okay? Now we do not leave it in this form, okay? Because remember that complex numbers have a real part and an imaginary part. So we rewrite this as two fractions, 32 over 37 plus 7i over 37, or 7 over 37i, either of those. Probably putting the I off to the side makes better sense. Remember, if it's in the numerator, you can pull it off to the side. For example, if it was 7x over 37, this is 7 over 37x. You can pull that variable, if you will, out to the side. Okay, that's the end of our lecture. I'm sorry it was a long one, and I'm sorry for the few typos in there. Hopefully they were explained, and reach out if you need any help.